Imagine traveling to the most distant place that exists, the edge of the universe we can see. It's 93 billion light-years away, a journey so long that our minds can't truly understand it. There, at the edges of known space, exist the first galaxies ever born, places where time works differently and the light from ancient stars is still traveling to us. But here's what's most impressive. Beyond this limit, there's an unexplored universe that could be infinite, full of mysteries we'll never be able to see. What exists in these hidden regions of the cosmos? What secrets does the universe keep beyond what our most powerful telescopes can reach? Tonight, we'll make this impossible journey together, exploring the most distant and mysterious corners of space, discovering cosmic wonders while you relax and let your mind float through the far reaches of the universe. Subscribe to the channel, leave your like and comment from which part of the world you're watching, get comfortable and relax. Let's begin. Have you ever wondered just how far out into space we can actually see with our telescopes? When we look up at a clear night sky, it's easy to feel like the universe stretches on forever. But in truth, there is a limit, a line that marks the edge of our cosmic vision. This is known as the observable universe. It's a kind of cosmic bubble surrounding us, representing the farthest distances from which light has had just enough time to reach us since the very beginning of everything, the event known as the Big Bang. Anything farther out remains hidden, completely out of reach, because the light from there simply has not arrived yet. This whole idea of the observable universe is not just about how good our telescopes are or how smart our scientists have become. Instead, it's rooted in the simple, stubborn speed limit set by the universe itself. Light, including all forms of electromagnetic radiation we use to see into space, can only travel so fast. The most precise way to say it is, the speed of light is the maximum speed possible, roughly 300,000 kilometers per second. Even with that incredible velocity, light takes a huge amount of time to cross the immense distances of the cosmos. So, when astronomers calculate the size of the observable universe, they are actually working out how far light could possibly have traveled since the Big Bang, which happened around 13.8 billion years ago. It's tempting to think we could just multiply the age of the universe by the speed of light to get the radius of this cosmic sphere. But there's a twist. Because the universe is expanding as light travels through it, those objects whose light is just now reaching us are actually much farther away now than when the light first left them. This is why the observable universe's diameter is not just a simple 27.6 billion light-years across, but more like 93 billion light-years. That's 93 billion light-years from one end to the other, a number so big it's hard for us to really picture. Within this mind-boggling volume exists everything we are able to gather information about. There are likely more than 2 trillion galaxies in this patch of the universe, and each of those galaxies can contain hundreds of billions of stars of their own. Wrap your head around this for a moment. We are just one planet, orbiting one star, in a galaxy that itself is only one among hundreds of billions. And that's just in the patch where the light has reached us. The cosmic ocean beyond remains an untouchable mystery. To actually make sense of all this, scientists rely on some of the most advanced instruments humanity has ever built. Telescopes like Hubble and more recently the James Webb Space Telescope have given us the deepest views ever, peering all the way back toward the beginning of the universe. But in a strange and fascinating way, looking into deep space is also looking back in time. That's because the farther away an object is, the longer its light has taken to arrive at Earth. When we look at a galaxy that sits 10 billion light-years away, we aren't seeing it as it exists today. We're seeing it as it was 10 billion years ago. This cosmic time machine effect means that telescopes don't just let us see farther, they let us observe the past. At the ultimate edge of the observable universe, we come to a place where time and distance start to lose their usual meaning. The light that comes from this distance is so stretched out and faint, it's at the limits of what we can detect. This edge isn't a solid barrier, like hitting a cosmic wall. It's more like a fog that gradually thickens, blurring our view as we get closer to the beginning of time itself. What lies beyond that fog is forever hidden from us, not because we don't have good enough technology, but because even if we waited forever, the light from those regions will never arrive. Why does all of this matter so much? The observable universe forms the only testable limit of our knowledge of the cosmos. It's the universe as we can truly, physically know it. Everything we understand about galaxies, stars, planets, cosmic structure, and the background radiation that fills space is all learned from what sits inside this enormous but finite sphere. If something lies beyond it, we can only theorize. It will remain outside the reach of observation or experiment. But the cosmic horizon, as scientists call it, is not just a limit, it's a clue. The fact that there's a horizon at all shows us how tightly the universe's history, its age, its rate of expansion, and the speed of light are all woven together. The expansion of the universe, first discovered by Edwin Hubble in the early 20th century, means that distant galaxies are always racing away from us. The farther a galaxy is, the faster it appears to recede. This means some galaxies move away so rapidly that their light may never actually reach us. They've crossed an invisible line where the expansion of space itself outpaces the speed of light relative to our point of view. Our observable universe is not fixed or universal. It depends completely on our position in space and time. If someone 100 million light years away somehow watched our universe, they would see a different patch of galaxies at the edge, their own personal observable universe. In a sense, each being in the universe has a slightly different bubble, but within each bubble, the structure and history of the cosmos tell an astonishingly consistent story. Getting a handle on just how much exists inside our observable universe is a challenge even for scientists. Imagine writing out a number as enormous as the estimated number of stars, something like 70 sextillion, which is a 70 followed by 21 zeros. It is a number so huge our daily lives offer nothing to compare it to. Then consider, on top of this, there are potentially even more planets, asteroid belts, comets, dust clouds, and maybe entire regions of space we have not noticed yet because their light has not yet reached us or is too faint for our best detectors. What holds all of these galaxies, stars, and planets together? The same laws of physics seem to work across the universe, at least as far as we can tell. Gravity is in charge, pulling together great clouds of gas that ignite as stars, clustering galaxies into rich tapestries, even binding enormous superclusters. The same matter, energy and physical constants that make up everything we see here on Earth appear to operate at the deepest reaches of the cosmos. That sense of order is actually reassuring. It means the universe is governed by rules we have a shot at understanding. The notion of the observable universe stems from the Big Bang theory, which tells us that the universe had a very hot, very dense beginning and has been expanding ever since. As the universe expanded, it cooled, and light became able to travel freely through space for the first time. This moment, called recombination, happened around 380,000 years after the Big Bang. The oldest light we can see, the cosmic microwave background, dates to this era. Anything that may have happened in this mysterious period before light could travel is forever cut off from view. It's not easy to visualize just how vast 93 billion light years actually is. A single light year is how far light can travel in 1 year, about 9.5 trillion kilometers. Multiply that by 93 billion, and what we have is a region so enormous the mind simply collapses under the arithmetic. And yet, compared to what might lie beyond this cosmic boundary, it could be just a tiny piece. Life inside the observable universe is all we will ever be able to study in detail, at least with today's laws of physics. The expansion of the universe even creates a stranger effect. As time moves forward, more of the universe actually slips beyond our cosmic horizon. Light from very distant galaxies we see now will one day be too stretched out, unable to reach us in the distant future. The cosmic horizon is always on the move, a dynamic, shifting boundary between the known and the unknowable. One of the wild facts about our universe is that the expansion of space can make it seem like some objects recede from us faster than the speed of light. This doesn't break the speed of light barrier because it's space itself expanding, not the objects zipping through space. It's a subtle but crucial point. That's why when we talk about the edge of the observable universe, we are talking about the limits set by the expansion rate combined with the speed of light and the age of the universe. Nothing breaks the fundamental rules, but the universe is clever about the loopholes. When we talk about the observable universe, we should also remember that the edge isn't a physical place. It's not as though if you were to travel far enough, you'd hit a wall or a barrier. The edge is defined by the farthest light we can possibly see. It is a horizon, just like the one you see when you look out to sea or across a flat plain. As time moves forward, that horizon may change, partly because the universe is getting older, and more light has time to reach us, but expansion also pushes it away in a cosmic tug-of-war. All the cosmic detective work we do relies on peering as close to the edge of this horizon as possible. Astronomers use powerful telescopes in space and on mountaintops, collecting light that left distant galaxies billions of years ago. When they look at these distant objects, they are looking at the universe as it was long before the Earth. Even the sun was born. That's what makes every new astronomical discovery a kind of time capsule, preserving a record of moments long gone. In its deepest sense, the boundary of the observable universe challenges our sense of reality. What does it mean if there are regions we can never see, never know, never interact with? For now, all scientific tests, measurements, and predictions must stay inside this boundary. The observable universe is our laboratory, our window into the workings of space, time, and the matter that they weave together. From a practical perspective, the observable universe is the grand arena where everything we understand about cosmology takes place. All the big mysteries, why the universe is expanding, how galaxies form and change, what dark matter and dark energy really are, unfold within this space. Whether it's mapping the distribution of galaxies, tracing the echo of ancient light, or searching for the faintest signals from the dark ages, every effort happens within the limits set by our cosmic horizon. Each leap in observational technology, from the invention of the telescope by Galileo in the early 17th century to the space telescopes of today, has pushed the boundaries outward. With every new discovery, our observable universe has grown, not in actual size, but in the amount of detail, depth, and richness we can perceive. We now find ourselves living at a unique moment in cosmic history, one where we are able to see both young and old galaxies, witness the afterglow of the Big Bang, and map out the web of galaxies, clusters, and voids that make up the universe. For scientists, defining the limits of our knowledge is almost as important as making new discoveries. The observable universe is not just a catalogue of contents, but also a marker for our place within the grand scheme of things. It reminds us of how much we can know, but also how much will always be out of reach. In this space, the known and the unknown are separated by the uncompromising laws of physics. The bigger question that follows naturally is, what does this mean for us, stuck here on our small planet orbiting an ordinary star? Knowing the size and scope of the observable universe brings perspective. It shrinks our everyday problems down to scale, but it also lifts up our sense of connection to a much greater story. If throughout all these billions of galaxies and trillions of stars, intelligent life has also looked up at its own sky and pondered the limits of observation, maybe we're participating in the grand tradition of cosmic curiosity. Our cosmic horizon will always be there. It will move outward as time goes on, but its existence is inevitable. It defines not just the size of the universe we can know, but the distance our curiosity can take us. Every photon of ancient light that falls into our telescopes, every faint signal caught from a distant galaxy, chips away at the edge of this boundary. In the process, it tells us not just about faraway places, but about the rules and history of reality itself. The observable universe is vast, structured, and governed by laws that we are only beginning to fully grasp. It is at once a source of awe, a puzzle to solve, and a challenge to our imagination. The cosmic horizon doesn't just limit us, it inspires us to ask what lies beyond, and challenges us to keep exploring as far as science and technology will allow. That's why defining our cosmic horizon and understanding the observable universe is so crucial for anyone who ever wondered what's out there, just beyond the edge of what we can see. Can you picture what it would really mean to journey across the full stretch of the observable universe, traveling from one end to the other, covering an unimaginable 93 billion light years? Most of us have a hard time wrapping our minds around numbers that big because they're so completely beyond anything we ever deal with in real life. But talking about this distance is absolutely necessary if we want to come anywhere close to understanding the true size of the universe that modern astronomy lets us see. The number itself, 93 billion light years, is already mind-blowing, but when you start to break down what's happening inside this expanse, things get even more fascinating. Imagine starting at some random spot, maybe on the edge of a galaxy, not so different from our own, and trying to travel from that side of the universe, across this biggest of all landscapes, to the opposite edge of space that we can possibly observe. First, it's important to get clear on what a light year actually is. A light year isn't a unit of time, it's a unit of distance, and it's the distance that light can travel in 1 year under normal conditions in vacuum. If you were to measure it as kilometers, that would be about 9.5 trillion kilometers for just 1 light year. Now, multiply that by 93 billion, and you can see right away the scale of the observable universe is absolutely massive in a way that almost defies the imagination. If you set out to cross it with a spaceship traveling at the speed of light, which is about 300,000 kilometers every second, you still wouldn't finish the journey in anything less than 93 billion years. For context, the universe itself is only about 13.8 billion years old, so just the idea of traveling that far already feels pretty wild. But there's something else to keep in mind. The universe is not just a flat or empty space, it's packed with structure and movement. That distance of 93 billion light years is not just a straight line like a road from your house to another city. Space itself is expanding as time goes on. This means that the galaxies and cosmic features you would encounter along the way are all moving apart from each other. And the farther you try to travel in your imagination, the more you have to account for how rapidly the universe itself is growing underneath you. The numbers get stretched by the very laws that shape the universe. If you could somehow watch this crossing play out, environment by environment, what would you see? Starting anywhere inside the universe, say Earth for example, you'd be surrounded by the nearest planets, stars, and then huge clouds of dust and gas. Climbing out of our local solar neighborhood, you'd pass through clusters of stars and then regions where stars thin out and dark space dominates. Pretty soon, you'd reach other star systems, then the outer parts of our own galaxy. The Milky Way is about 100,000 light-years across, which might sound enormous until you remember that the observable universe is almost 1,000,000 times wider than that. After clearing the edge of our galaxy, you would keep moving through intergalactic space. This is not empty, but it's much less densely packed than inside galaxies. You'd occasionally cross paths with wandering stars, gas, or even rogue planets that aren't orbiting any star at all. After a bit longer, you would start to enter regions around other galaxies, some similar to the Milky Way, and others much smaller or stranger in shape and scale. The closest large galaxy to us is Andromeda, which sits just over 2 million light-years away. Even at light speed, it would take more than 2 million years to get there from Earth. Beyond nearby galaxies, you would eventually head into larger cosmic structures called galaxy clusters. The Virgo cluster, for instance, is a gathering of more than 1,000 galaxies, gathered together by gravity in a loose but immense web. This starts to show just how much variety and structure there is on the way. Some regions are absolutely crammed with galaxies, while others are colossal voids, nearly empty spaces where only a few lonely galaxies or clouds of gas drift in the darkness. If you look at the large-scale structure of the universe as a whole, scientists call it the cosmic web. This web is made up of long filaments of galaxies and dark matter that connect into clusters and even larger superclusters, with enormous voids of emptiness scattered in between. On your journey across the universe, you'd be weaving your way through this complicated tapestry that nature put together over billions of years. Even at immense speeds, you'd alternate between bustling cosmic city centers and huge stretches of deep, quiet emptiness. It's a view that recent telescopic surveys like the Sloan Digital Sky Survey have made possible to trace, even if only with the light that reaches us and not by any physical travel. There's another detail. As you travel farther away from your starting point, you are also moving back in time. Every time you look deeper into the universe, you're seeing objects as they were further in the past because of the time it takes their light to reach your eyes or your telescope. That's a basic feature of how light works at these enormous scales. If you find yourself looking at a galaxy that is 10 billion light-years away, what you're really seeing is the light that left that galaxy 10 billion years ago, not what the galaxy looks like now. So your journey across the observable universe might not be a journey through simple distance, but also a journey through the timeline of cosmic history. Imagine how that timeline would play out along the trip. As you go further and further, let's say past the halfway point of your crossing, you're not just covering greater distance, but also looking at older and older epochs in cosmic evolution. Early galaxies were different. The further you move from us, the closer you get to the epoch when the first stars and galaxies formed after the Big Bang. These ancient structures were smaller, less organized, and sometimes just clumps of gas with a few bright hot stars lighting them up. If you pushed all the way to the extreme outer edge of the observable universe, you'd eventually see what astronomers call the cosmic microwave background, or CMB. This is the oldest light in the universe, which comes from a time about 380,000 years after the Big Bang. Before then, the universe was so hot and dense that light itself couldn't travel freely. The CMB is a sort of wall for our observations. No matter how hard we try, we can't see through it to anything earlier using regular telescopes. Throughout this journey, you would also notice another crucial cosmic fact. Space is not standing still. Because of the ongoing expansion of the universe, galaxies that are far away appear to be racing away faster and faster. In some places, this recession velocity is so great that, based on our calculations, the light from those galaxies will eventually never reach us. Right now, some galaxies at the very edge of the observable universe are already moving away at what appears to be speeds faster than light itself, not because they're moving through space at that speed, but because space itself is stretching between us and them. This expansion is governed by the rate known as the Hubble constant, named after the astronomer Edwin Hubble, who first noticed in the 1920s that distant galaxies are moving away from us and from each other. The faster a galaxy is receding from us, the farther away it appears. All of this comes together to explain why we are only able to see so far, because beyond the observable horizon, things are receding so quickly that their light, no matter how long we wait, will never reach us. A journey across these distances forces us to reconsider what distance and location even mean in space. In the universe, things aren't arranged like dots on a map that you can go between in a straight line. Instead, the geometry of space itself is curved by matter, energy, and the ongoing expansion. This means the numbers we use, like 93 billion light years, are not just a ruler stretched across empty space, but the result of really complicated measurements of how objects move and how their light changes as it comes to us, thanks to cosmic redshift. This redshift is the stretching out of light waves as objects move away from us, which makes their light appear redder than it otherwise would. By measuring redshift, astronomers can tell how far away a galaxy is and how fast it's moving. The farther across the universe you try to travel, the more this expansion adds up. Close to home, it's almost not noticeable, but by the time you reach billions of light years, galaxies become smeared out, light is stretched, and objects become harder to spot. Some of the farthest objects we've detected are ancient galaxies and gamma-ray bursts, as well as the first light after the Big Bang. Our telescopes, especially ones like Hubble and the James Webb Space Telescope, have managed to glimpse objects more than 13 billion light-years away, which means we are seeing them as they were less than a billion years after the universe began. Each step farther is a step back in time, and only the brightest or most energetic events can reach us across all that space. If you were on this journey, you would see the diversity of environments increase dramatically as you went along. Closer to where we are now, there is a lot of structure: spiral galaxies, elliptical galaxies, galactic clusters, and all their dynamics. As you look further and further back, galaxies would look smaller, fuzzier, and redder until you reach the deep fog of the CMB, which bathes the universe with faint, cool microwave radiation. That horizon is the final snapshot of the early universe, a faint afterglow frozen in time since 380,000 years after the birth of the cosmos. What about all the stuff in between? Between regions of dense galaxies are massive voids, literally hundreds of millions of light years across. With so few galaxies, they're mostly empty on cosmic standards. These voids are balanced out by filaments and walls of galaxies, making the whole universe resemble a kind of giant web. Studies of large-scale cosmic structure have revealed that this web shape is not random. It's formed by gravity, dark matter, and the expansion of space itself. The universe is packed with spectacular sights, but also huge stretches where not much happens at all. There are also the objects we can barely detect or not at all, like dark matter and dark energy, which make up the majority of the mass and energy in the universe. As you cross the universe, these forms of invisible matter and strange energy would shape your journey in ways you wouldn't see but could measure by their gravitational influence. For instance, dark matter keeps galaxies together and adds weight to clusters, while dark energy is what's driving the accelerated expansion of space, making the journey itself more difficult with every passing epoch. If you try to visualize your journey in terms of Earth days, years, or even centuries, every time frame you can think of just falls short compared to the scale of what you're up against. Let's say you could travel at 10 times the speed of our fastest spacecraft ever built, something like the Parker Solar Probe, which goes at about 700,000 kilometers per hour. That still wouldn't be enough. You'd need almost impossible economies of speed just to cross from one local group of galaxies to the next, let alone all the way across the cosmic web and into the dawn of time. Most scientists will tell you that for now, imagining travel across the observable universe is really a way of describing what we see with light, not with spaceships. Each increase in distance lets us piece together how the universe evolved, how matter clumped together, how stars and galaxies ignited, and how they organized into the larger structures we see today. When scientists talk about seeing 93 billion light years across, it's less about physical travel and more about tracing light, signals, and information from one era to another, connecting the ancient past with the present. The ability to see across these mind-bending distances comes down to a combination of technology, physical law, and a bit of good luck. Our planet happens to sit in a pretty quiet part of the galaxy, without too much dust or bright interference to block our view. Our instruments are able to pick up faint photons of light that have traveled for most of the history of the universe without being disrupted. Even so, there are limits. Light can be absorbed, scattered or blocked, and some events send out their signals in forms beyond visible light, like radio waves, X-rays, and even gravitational waves. As research continues, astronomers are not just using light, but also signals like neutrinos and ripples in space called gravitational waves to observe things happening across the cosmos. These are new ways of extending our view, but they still come up against the ultimate barrier, the finite age and expanding nature of the universe. No matter how clever we get, the number 93 billion light-years will always mark the limit for the observable universe as seen from Earth right now. When you break down this journey, each step along the way tells a different part of the story. It's a tour through the cosmic neighborhood, across the galaxy, out past local groups, through clusters, into voids, along filaments, then through walls of galaxies, all the way to the edge where only the faintest echoes of creation remain. The deeper you look, the less familiar things become, the more alien cosmic history seems, and the harder it is to pull consistent information from what little remains of those ancient eras. Even so, this tour across cosmic distance puts everything in perspective. Our planet, our solar system, our galaxy, they all fit comfortably inside just a tiny corner of this cosmic web. We're only able to see so much because of the perfect balance between the universe's age, the speed of light, and our patch of the cosmos's history. There's likely much more beyond the horizon, but for now, 93 billion light-years is the greatest distance we can probe with science. This is what makes studying the journey across the observable universe truly amazing. It's a combination of physics, history, and cosmic geography, all coming together to help us figure out how big and diverse the universe truly is. From nearby stars to remote clusters, from bright young galaxies to faint ancient light, every distance reveals something new. And travelling it, at least with our minds and our telescopes, reminds us just how grand the cosmos can really be. As you keep looking deeper into space and further back in time, there's a special point where something truly unique begins to appear. The very first galaxies. These ancient objects sit right at the reach of the most powerful telescopes ever built, and their faint light tells a story about how the universe started turning from simple, dark, and empty to the crowded and colourful place it is today. When astronomers talk about the birth of galaxies, they're talking about an era called cosmic dawn. This is a period that began just a few 100 million years after the Big Bang. Imagine that, less than 1 billion years into the universe's entire 13.8 billion year history. And already, the seeds for all the galaxies we see now are starting to form. The earliest galaxies are so distant from us that we can only catch a glimpse of their ancient light by collecting the faintest signals possible. The universe didn't always have structure, go back to its very beginning, and it was just an extremely hot, dense soup of particles and radiation. It took hundreds of thousands of years for the universe to cool down enough for particles to glue together and form atoms. For a long time after that, everything was filled with hydrogen hydrogen and helium, but it was dark. There were no stars or galaxies yet. This long phase is easy to miss since we're looking so far back in time. What changed everything was when gravity started pulling together the first clouds of gas. These clouds began to collapse into denser regions under their own weight, and that's when the first stars ignited. These first stars weren't like the ones shining in our night sky right now. Scientists think they were made almost entirely of hydrogen, and they were much bigger and hotter, sometimes a few hundred times the mass of the sun. Because they burned so bright, they didn't last long, and when they exploded at the end of their lives, they released a ton of energy that changed the environment around them. Grouped together, these first generations of stars came together under gravity to create the earliest galaxies, turning some of the universe's first dark spots into places full of light. When we look for these first galaxies, we're trying to capture light that has traveled billions of years to reach us. Since the universe has expanded during that time, the light gets stretched, becoming redder, a phenomenon known as redshift. The galaxies from cosmic dawn are incredibly faint, and by the time their light makes it to Earth, it's shifted so far into the infrared that only ultra-sensitive instruments like the James Webb Space Telescope can even spot them. Some of the most distant confirmed galaxies astronomers have seen are at a redshift greater than 11, which means their light has taken more than 13 billion years to reach us. Just detecting this light is a major accomplishment and tells us we're seeing galaxies almost as old as the universe itself. Studying these primordial galaxies is like having a time machine for the history of everything. They show up as tiny smudges or dots in telescope images, sometimes so faint that it takes days or weeks of observation just to confirm they're there. Still, even in these blurry shapes, scientists can uncover a lot. For instance, those early galaxies tend to look smaller and less organized than later ones. They often don't have the beautiful spirals or strong regular structures that galaxies like the Milky Way have today. Instead, the galaxies from the dawn era are clumpier, more like rough clouds packed with lots of young, massive stars, making them shine with ultraviolet and eventually infrared light. Finding out how these galaxies formed is a huge part of understanding why the universe looks the way it does now. The process is almost entirely about gravity pulling in gas, causing pockets to become denser and stars to begin shining in large groups. Over time, these small groups of newborn stars merged with others, piling up more material, and slowly built the bigger and more organized galaxies. In some cases, early galaxies collided or merged, making even larger and more complex structures. This cycle of growth, from tiny beginnings to sprawling clusters, still happens on some level in the universe even now. But during cosmic dawn, it was happening all over the place, and at an extraordinary pace. One of the mysteries astronomers have tried to solve by watching these early galaxies is how quickly the universe switched from being full of neutral hydrogen to being ionized and transparent, the so-called epoch of rionization. Before the first stars and galaxies kicked on, the universe was pretty much dark because that neutral hydrogen gas blocked light from traveling far. But when the earliest stars lit up, their powerful radiation started to clear away the fog, breaking apart hydrogen atoms and making the universe transparent. By finding and studying galaxies from this time, scientists can track how rionization spread, helping to pin down when and how the cosmic fog lifted for good. There's also a lot of excitement about what these galaxies tell us about the recipe of the universe at that time. Because the first stars were mostly massive and short-lived, they created the first heavy elements, the ones like carbon, oxygen, and iron that are necessary to build planets and, eventually, life. The earliest galaxies are the places where this cosmic alchemy started. When these first giant stars exploded, they scattered heavier elements out into space, seeding the next generations of stars and galaxies with more ingredients, which eventually ended up in places like our own solar system. This means that the ancient galaxies we study really did shape the future of the whole cosmos, even shaping the ingredients that make up our planet. The work to find and understand early galaxies is a real technical challenge. It takes extremely sensitive detectors, careful analysis of faint signals, and often years of work by teams around the world. When new deep sky surveys are made, astronomers comb through huge amounts of data just to find a handful of candidate galaxies from this period. Confirming them often involves comparing images at different wavelengths, visible, infrared, even radio waves, to make sure the signals line up with what we'd expect from such distance and age. Many of the details about these galaxies come from looking at their color and brightness across different bands of light. When astronomers find a sharp drop-off in brightness between certain filters, called a Lyman break, that's a big indication the light comes from very early, distant galaxies. Each new detection gives us a better sense of how galaxies evolved, grew, and changed over cosmic time. Another clue from these first galaxies is the role of dark matter, a form of matter that doesn't emit or absorb light, but does have mass and exerts a gravitational pull. Without dark matter, the gas clouds in the early universe wouldn't have clumped together fast enough to make stars and galaxies as early as they did. Simulations and observations suggest that every galaxy, even the earliest ones, formed inside vast halos of dark matter. That means the structure of the universe we see, right down to the clusters and superclusters of galaxies, was shaped by something we can only measure indirectly. A surprising finding is just how quickly the first galaxies appeared after the Big Bang. For a long time, astronomers thought it should take at least 1 billion years before any galaxies showed up. Recent discoveries, though, are showing small galaxies turning up as early as 200 million years after the universe started. This rapid emergence has led scientists to rethink how fast gas can cool and collapse, and how quickly stars could form in these early environments. And it's not just about timing. Scientists use what they can see in these early galaxies to learn about big forces at work in the universe. For example, the shapes and sizes of galaxies can hint at the role of cosmic inflation, a period of superfast expansion just after the Big Bang that set the stage for how matter and energy would clump together. Looking for certain patterns or concentrations in early galaxies helps test theories about inflation and the basic structure of space and time. The story from cosmic dawn is still being written. Every new observation, each time a telescope picks up the red signal of a distant, newly discovered galaxy, pushes back the frontier a little further. It's a slow but steady process, putting together bits of evidence until a clearer picture forms of how the universe made its first great leap from darkness to the complex structures we see today. Galaxies are not simple or static. Even the smallest and earliest ones were bursting with activity. Some had areas where stars were forming at rates far higher than anything seen in most present-day galaxies. This intense activity often triggered wild environments with supernovae going off, gas clouds getting blasted apart, and sometimes new black holes forming at the centers. All these processes helped mix and move the material in these young galaxies, making sure that the next generations of stars would start with a wider mix of elements and possibilities. Over hundreds of millions of years, the simple, early galaxies kept growing by merging together or swallowing small clumps of gas and stars nearby. This building up process is called hierarchical growth. Each merger made galaxies bigger and sometimes more structured, and it led to the wide range of galaxy shapes we see in the later universe. Around this time, the first large clusters of galaxies began to gather. The cosmic web of filaments and voids started to become recognizable, and the universe slowly became a place where structure ruled over emptiness. Advances in technology have been a huge help for this field. The Hubble Space Telescope, for example, gave us our first close-up looks at galaxies from only a few 100 million years after the Big Bang. With the launch of the James Webb Space Telescope, astronomers are pushing even further back, regularly spotting galaxies at redshifts previously unreachable with older equipment. With every improvement in detector quality, sensitivity, and survey size, a few more clues are uncovered, and the portrait of the early universe gets a little sharper. Some galaxies from the early stages of cosmic dawn have already shown scientists things they didn't expect. A big surprise has been the discovery of rather massive galaxies forming very early, challenging the best ideas about how fast stars and structures could pull together. The size and brightness of some of these newly discovered ancient galaxies, some only 300 or 400 million years after the Big Bang, have caused many experts to go back to their models, re-examining just how quickly matter can assemble under gravity and how fast the first heavy elements could be made. The search for early galaxies isn't only about light either. Some astronomers are investigating how energetic jets, gamma-ray bursts, or radio signals could hint at activity in the very first massive stars and black holes. By monitoring for faint signals in a variety of frequencies, researchers hope to catch signs of the most dramatic events in the young universe, like the birth of supermassive black holes in the centers of growing galaxies. The conditions inside the earliest galaxies also tie into questions about the origins of planets and life. The heavy elements produced by first-generation stars are crucial for forming rocky worlds. Without those elements, you can't get solid planets, and probably can't have chemistry complex enough for life as we know it. So by studying how and when the first galaxies kicked off the cycle of star birth, death, and rebirth, astronomers are actually tracking the start of the long chain that led not just to our solar system, but to the basics needed for life to appear anywhere. Cosmic dawn is when the universe went from being places of mostly gas to places rich with light, heavy elements, star clusters, and all the building blocks for future galaxies. As these earliest galaxies evolved, they set the standard for the following billions of years of development, all the way up to galaxies in our current time with their complex shapes and rich chemistry. There's an entire team effort involved in piecing this together. Astronomers, data scientists, engineers, and theorists pool their skills to make sense out of tiny pinpricks of data, push instruments to their limits, and create the computer models needed to simulate such distant, challenging environments. By comparing what gets observed through the lens of today's best telescopes with large-scale simulations run on supercomputers, the field constantly refines our view of cosmic dawn and the earliest times. More surprises will probably keep coming as technology improves and new ways of observing distant light become possible. Each step closer to the Big Bang means looking for even smaller, dimmer, and more scattered galaxies. Proof of when the very first stars flickered to life and how quickly they transformed the universe is going to keep unfolding year by year as projects add more data, improve analysis, and, with every deep survey, catch a few dozen more of these relic galaxies. For now, though, everything we understand about the beginnings of galaxies points to one thing. The universe started small, dark, and simple. But, through very ordinary physical processes, gravity, radiation, nuclear fusion, the first real cosmic structures appeared incredibly quickly. Those early galaxies, full of massive short-lived stars, made the first heavy elements, brightened the universe, and started the slow journey from ancient darkness to the light and variety we see across space today. The work to examine and reconstruct this time remains one of astronomy's most exciting frontiers. Every newly identified distant galaxy becomes another data point in the universe's own family album, catching it during its wild, energetic, and unpredictable childhood. All the work being done to observe those distant early galaxies depends on one key fact about the universe. Looking farther out means looking deeper into the past. That's not just true for astronomy, it's a direct consequence of how light travels and how time and space are connected. When we say we're seeing a galaxy as it was more than 13 billion years ago, what we're really saying is that the light has been traveling all that time before finally arriving at our telescopes. This idea leads us into a tricky but fascinating part of physics, where the way we usually talk about time turns out to be only one version of a much more complicated story. At larger scales, and especially when you start talking about the edge of the observable universe or the highest gravitational fields, time doesn't act in the straightforward way you might expect from clocks or calendars. When light leaves a distant galaxy, it starts out on a journey that can take billions of years. For us, it's almost like opening a window into the long-gone past of that galaxy. Space and time aren't static. They constantly change depending on factors like speed and gravity. This is where Albert Einstein's big discovery, the theory of relativity, comes in. Relativity reveals that time can stretch or squish based on either how fast something is moving or how much gravity is around. On Earth, these effects are so small you never have to think about them in daily life. But in the cosmos, in situations involving galaxies speeding away or giant clusters where gravity is strong, they matter a lot. Astronomers always keep the concept of redshift in mind while studying distant objects. The basic idea is that as the universe expands, the light from faraway things gets stretched out along with space itself. This stretches the waves, turning them redder, which we call redshifting. But it also means that the farther back in time you look, the more extreme these effects get. It doesn't just change the appearance of light, it actually changes how we measure the time when events occurred. Sometimes a burst of energy or an explosion in a remote galaxy might take much longer to play out according to our clocks here on Earth than it would appear to someone who was actually there. The elapsed time gets extended from our point of view, a direct illustration of what's called time dilation. Time dilation can happen through two separate but connected effects, one tied to velocity, the other to gravity. The first is called special relativity, discovered by Einstein in the early 1900s. If something moves close to the speed of light, say a cosmic ray or particle zipping across space, its own perception of time slows down compared to what a person at rest would see. For galaxies at the edge of the observable universe, this means that processes such as star formation or the way that light changes as it leaves them all seem to run a little slower, as measured by us here and now. The second effect kicks in when gravity gravity is hugely strong. This is called general relativity, which describes how gravity itself warps space-time. Near a black hole or inside a giant galaxy cluster, gravity is so powerful it actually bends time, causing a clock near the massive object to tick more slowly than a clock in emptier space. Even on Earth, this happens to a tiny degree. The clocks on satellites have to be adjusted because they're in a slightly weaker gravitational field than clocks on the surface, or their timing would drift. But multiply the effect up to cosmic scales and the results get dramatic. Signal timings, the rate of star formation, even the light from supernovae, all get stretched just because of how gravity bends both space and time. The universe's expansion doubles down on the weirdness of time. Because all galaxies in distant regions are moving away from us, the time it takes for their light to reach us keeps increasing. If you want to compare clocks, one in a young, just-formed galaxy at the far edge, and one on Earth right now, you can't just rely on simple calendar math. Instead, astronomers use complex formulas to translate the timescales. An event that takes place in a distant galaxy at a certain redshift appears to take a lot longer to play out for us, looking in from across expanding space. This isn't just a curious detail, it's central to understanding cosmic history. Observing a supernova, a gamma-ray burst, or the changing brightness of a quasar means we're seeing those events on a clock that runs differently than ours, simply because of how far their light has travelled and how the universe has stretched in the meantime. With all these stretchings and squishings, you may wonder how anyone keeps track of when everything happened. Astronomers use a toolkit of distances and timescales like look-back time, how long ago the light set out on its journey, or cosmic time, which is like the master clock for the universe, starting from the Big Bang. For any object we see out in the cosmos, the light's journey time, the expansion rate of the universe, and its redshift all have to be pieced together. It's almost like solving a puzzle backward, using what we see now to reconstruct not just where and when something existed, but how quickly or slowly its changes unfolded along the way. Another important point is that as you look further out, the time gap between then and now widens dramatically. When we look at a galaxy 8 billion light-years away, the universe itself was much younger. Stars were forming at higher rates, galaxies had different shapes, and the chemical content was simpler. To study the evolution of these objects, astronomers need models that accurately reconstruct how their clocks have ticked over cosmic time. Comparing these ancient clocks to our Earth-based reference is one of the keys to figuring out things like the age of the universe, the flow of cosmic history, and even the ultimate fate of everything. Another effect is that as distances increase, the relative motion of galaxies becomes significant. Almost all distant galaxies are moving away from us because of continuing expansion. Some are receding so fast that their light will never catch up and reach Earth at all. This has a subtle impact on time as well, because the fabric of space itself is expanding, not just the motion of any particular object. When astronomers measure how long it takes for light or signals to reach them, they have to include both time dilation from speed and the stretching caused by space's growth. Closer to home, effects from relativity happen on much smaller scales. On Earth, if you take very sensitive atomic clocks and put one on top of a mountain and another at sea level, the one at higher altitude ticks a bit faster because it's farther from the center of gravity. These practical demonstrations are tiny compared to what goes on in the universe at large, but they're easy to relate to and help explain how cosmic scale time effects work. If you think about how these effects compound over billions of years and billions of light years, the overall result is that the very concept of now stops having a universal meaning. An event, like a star exploding in a faraway galaxy, is both happening and has already happened, depending on where you stand. Scientists are used to talking about the universe today, but what that really means depends on your position and your frame of reference, including the impact of gravity and cosmic expansion on your measurements. Another interesting aspect of time in the universe is how it changes depending on local versus cosmic conditions. The center of a massive galaxy cluster is so dense that time there actually passes measurably slower than in emptier regions of space. Over millions or billions of years, this becomes a practical factor in modeling galaxy evolution, star life cycles, and how black holes swallow up material. The more gravity, the slower the clock. If you compare time passage at the edge of a huge supercluster to that of a quiet patch of intergalactic space, the difference really adds up. All these concepts come together in the way cosmologists piece together the big picture. They use what's called the cosmological principle to assume that on the largest scales, the universe is roughly the same everywhere, everywhere. That lets them draw broad conclusions from whatever part of the sky they observe, as long as they keep these effects of time dilation, expansion, and gravity in mind. Without accounting for all these quirks of cosmic time, measurements would never match up, and we'd have no chance of tracing how galaxies evolved, how the cosmic web formed, or even what the true sequence of cosmic events is supposed to be. There is a special moment in cosmic time called the surface of last scattering, which is when the universe cooled down enough for light to travel freely. This moment, about 380,000 years after the Big Bang, marks the oldest light we can see, the cosmic microwave background. Calculating when we're seeing depends on all the time stretching, all the expansion, and all the relativity that have happened since. The fact that we can spot it at all and date it so precisely shows how well science has worked out the universe's clock. Relativity also comes into play when looking at extreme events, like the merging of black holes or neutron stars. When these ultra-dense objects collide, they send out ripples in space called gravitational waves. Instruments like LIGO and Virgo have managed to detect these waves, and the timing of their arrival has to factor in both the stretching of space over billions of years and the way gravity warps time right near the source. These observations give direct proof of the reality of cosmic time dilation, and they help scientists test the core ideas of relativity on the grandest possible scale. One of the most practical uses for understanding cosmic time dilation is in measuring the real age of distant objects. Without factoring in these effects, we'd end up with numbers that don't add up. For example, supernovae, exploding stars, are used as standard candles by astronomers to measure distance. If they appear to last longer or shorter than expected, it's usually because their light has been stretched out by both expansion and gravity along the way. Making sense of these observations is essential for calculating things like the rate at which the universe is expanding, known as the Hubble constant, and it feeds directly into our models about the past and future of space. A surprising thing to consider is that, because of cosmic expansion, some galaxies we see today are actually much farther away now than when their light left them. For the most distant ones, it's possible that even as their ancient light just reaches us, those galaxies are now well beyond the observable universe, forever out of reach for new signals. This moving horizon is a direct result of changing time and distance across billions of years. It highlights how deeply interwoven time and space are in the grand design of the cosmos. All these strange behaviors of time don't break the fundamental rules of science, but they do remind us that our everyday experience isn't enough to explain what goes on at universe's largest scales. Physicists and astronomers have built up detailed ways of measuring time that agree with relativity's predictions, and all observations so far have matched up. The math is complex, but the basic principles always hold. The faster something moves, or the stronger the gravity, the slower time ticks for it compared to other places and speeds. And over the staggeringly long times of cosmic history, from the Big Bang to the birth of our own solar system to the present day, these effects add up. One of the key achievements of modern cosmology is that it's managed to line up all these time-related measurements into a unified story. From the moments right after the Big Bang, when the universe was so hot and dense that time itself was almost meaningless, all the way to now, with galaxies flying apart at incredible speeds, scientists can reconstruct what happened and when by adding up light travel time, redshift, time dilation, and all the other ingredients. This is how we can say with real confidence that the universe is about 13.8 billion years old, an age that comes from fitting together all the different clocks and timers the universe offers us. The mathematics behind this is handled by things like cosmological redshift equations, space-time diagrams, and models of universal expansion, but even people not doing the math can appreciate the end results. When you see pictures of galaxies labelled as being 12 billion light-years away, or watch a video of a simulation showing the universe's growth, you're actually seeing predictions made possible by combining all our understanding of time, light, distance, and gravity into one consistent picture. Moving deeper into the details, even phenomena like cosmic lenses, where gravity from a massive object bends and magnifies the light from objects behind it, owe some of their strangeness to the warping of time. Light's path isn't just stretched through space, but slowed down by the increased gravity, turning what looks like a simple magnification into a record of different tempo clocks from different parts of the universe layered together. So, in observing galaxies, supernovae, or even planets forming around distant stars, astronomers always need to reset their sense of timing to match the time frame each object presents. This ensures measurements line up, distances are real, and the sequence of cosmic events makes sense. Every advance in technology that brings us closer to the edge of the universe increases the need to get these calculations right, because at extreme distances and ages, time is always running on a different cosmic schedule. With these time effects in mind, even new discoveries about the earliest epochs, the birth of galaxies, the formation of the cosmic web, the faint signals from the cosmic microwave background, can be carefully slotted into their proper place in the universe's clock. This is what lets scientists keep refining the history book of the cosmos, always adjusting for relativity, expansion, and gravitational effects to get ever closer to a true story of how the universe unfolded. All things considered, time in the cosmos is much more than what we measure on watches or calendars. It's an elastic, continually shifting dimension that ties every cosmic event to a specific place in the universe's ever-expanding history. That elastic, ever-shifting concept of time and space across the universe finds its most striking example in a discovery that changed everything we know about where the cosmos came from: the cosmic microwave background. This faint glow is the oldest light that astronomers can observe, a silent and persistent radio signal that fills the entire sky and reaches us from every direction, no matter where we look. It's sometimes described as the universe's first baby picture, capturing a moment only about 380,000 years after the Big Bang, when conditions changed so dramatically that light was allowed, for the first time ever, to travel freely across space. Before this point in the universe's timeline, space was completely packed with free-moving electrons, protons, and other particles bouncing off each other in a hot, dense fog. Photons, particles of light, couldn't travel very far at all before being scattered by these particles. The whole cosmos was basically opaque, like a thick cloud with no way for light to escape. When people refer to the surface of last scattering, they mean the moment in history when the universe had expanded and cooled enough so that those electrons and protons could finally stick together, forming neutral hydrogen atoms. Suddenly, the universe became transparent, and light from that instant could spread out unimpeded in all directions. That ancient light has been moving ever since, traveling billions of years across the stretching fabric of space, cooling and losing energy along the way until it reached us as a faint microwave signal. What's incredible is how carefully astronomers have managed to observe and measure this faint afterglow. The first crucial measurements came in the year 1964, when Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, found their radio telescope picking up an odd, persistent noise they couldn't explain. It turned out they had found the leftover heat radiation from the Big Bang, a faint background signal washing over the planet all the time. Since then, satellites and ground-based observatories have been built specifically to map the cosmic microwave background in ever finer detail, from the COBE satellite in the 1980s to WMAP, and finally the Planck spacecraft, which finished its most complete map in the past decade. All of these measurements point to one thing: the universe has the same faint microwave glow, just a few degrees above absolute zero, coming from every direction. At around 2.7 Kelvin, just 2.7 degrees above zero on the Kelvin scale, which is about minus 270 degrees Celsius or minus 454 degrees Fahrenheit, the temperature is shockingly cold. But what's so fascinating is that this radiation is almost perfectly uniform, with tiny, tiny variations in temperature, just 1 part in 100,000. It's these slight changes that tell the real story. Those minuscule temperature differences in the cosmic microwave background hold all kinds of evidence about the very early universe. They are tiny imprints left by quantum fluctuations in density and energy, magnified during the first frantic moments after the Big Bang, when cosmic inflation made the universe balloon in size. What we see today in galaxy clusters, cosmic voids, and the cosmic web all had their seeds in those minute fluctuations locked into the microwave background. The slightly denser regions acted as the starting points where gravity would later draw together clouds of gas, triggering the birth of stars and galaxies. Because the microwave background comes from such an early period, and because it fills the sky so evenly, it acts as a sort of edge or wall for visible information. There was no free-travelling light before this era, just constant bouncing and energy swapping. Any light or signal that tried to travel from earlier times was blocked or absorbed until the moment recombination happened and space became clear. Cosmologists use the microwave background as a standard reference point. By measuring it, they can determine both the age and the shape of the universe, and also figure out what it's made of. The precise pattern of those temperature ripples reveals the proportions of normal matter, and dark energy present in the cosmos. The power spectrum, a chart of the size and strength of those fluctuations across the sky, matches up beautifully with models of cosmic evolution. Scientists were even able to estimate that the age of the universe is about 13.8 billion years old using this data, cross-checked against other pieces of evidence like galaxy surveys and supernova distances. What's really impressive is how precisely instruments can map this ancient light now. The Planck satellite, for example, mapped the sky at multiple microwave frequencies with enough clarity that it could see variations as small as a few millionths of a degree across tiny patches of sky. These maps show a mottled, spotty texture, a kind of blueprint for everything that would happen in the universe afterward. If you take the map and run the clock forward using the laws of gravity, gas physics, and expansion, you end up recreating the distribution of galaxies and clusters that we see now. All of those swirling, luminous cosmic shapes were first planted as faint, subtle spots in the microwave background. The importance of the cosmic microwave background doesn't stop at just painting the big picture story. The background radiation contains information about the speed with which the universe expanded in its earliest moments, something called the Hubble constant. It gives clues about the overall flatness of the universe, how much dark matter is present, and even hints about particles that may be so elusive we haven't detected them directly, such as certain flavors of neutrinos. Cosmologists use math-heavy models to combine tiny differences in temperature and polarization in the microwave background with results from other fields, building an incredibly detailed, testable model of the universe. It's also worth noting that the microwave background is slightly polarized. This happens because, at the time that light was finally freed, the universe was full of expanding waves of pressure and matter, almost like sound waves ringing across space. The spreading light caught some of these patterns, passing them along as faint directional hints in the cosmic background signal. By carefully studying the polarization, scientists can learn even more about the earliest times, from conditions in the first fractions of a second after the Big Bang to how quickly the universe became Ryanized several 100 million years later. There's a limit to how much we can learn from the cosmic microwave background. It marks the farthest boundary for any regular kind of light. We can't see past it using even the best telescopes because before this time, space was simply not transparent. For anything earlier than 380,000 years after the universe began, astronomers must rely on clever indirect methods such as gravitational waves or high-energy particles to gather clues. The cosmic microwave background isn't uniform in another important way either. As light travels toward us, it passes through galaxy clusters that can twist, scatter, or slightly shift its energy. This gives cosmologists hints about intervening matter. By studying these secondary anisotropies, they can measure things like the motion of galaxy clusters, the amount of hot gas in the universe, and the presence of massive cosmic voids. In fact, some of the first solid evidence for the existence of dark matter and dark energy comes from observing how the cosmic microwave background interacts with large-scale structures as it crosses the cosmos. The original noise Penzias and Wilson discovered was so faint and constant they first suspected pigeon droppings in their equipment, but that stubborn background has since become the single best source for information about the universe's birth, geometry, fate, and inner composition. Each new round of observations peels away new details, allowing cosmologists to refine their models and think through new questions, such as, did cosmic inflation really happen? And if so, what drove it? Could there be tiny, fast-moving gravitational waves mixed into the background, too faint for us to pick up yet? Is the universe really totally uniform at the largest scales? Or are there chaos, cold spots, and always hot spots that break the rules? Other countries and international partnerships have joined in the hunt for microwave background data, not just with satellites, but with telescopes installed at the South Pole or on high mountain peaks. High-altitude observatories like the Atacama Cosmology Telescope or the South Pole Telescope get above much of the Earth's own microwave noise, giving them an especially clean view of this ancient radiation. Teams coordinate to compare data, check for errors, and rework findings when something new is noticed. That global effort is how scientists have been able to confirm, again and again, the Big Bang picture for the universe. Every independent check, across instruments, across continents, across technologies, matches up with the idea that the cosmos sprang from a hot, dense, rapidly expanding state and has been cooling and spreading out ever since. The differences measured in the cosmic microwave background have become the standard by which all other models are tested. Now, some of the latest science is focused on hunting for the smallest wrinkles in the background that might reveal unexpected physics. For example, some researchers are now hoping to pick out even tinier polarization signals, which could tell them about the exact conditions during cosmic inflation, the moment, just a trillionth of a second after the Big Bang, when the universe expanded faster than the speed of light itself. These polarization patterns, called B modes, are difficult to see because everyday sources of noise easily drown them out, but finding them would open up a whole new field of cosmic archaeology. Another area of research is into what might lie beyond the edge marked by the microwave background. Because no regular light from before this era can reach us, any information about earlier times must come from other sources, possibly gravitational waves from immense cosmic events, or rare cosmic particles that could slip through even the thick fog of the early universe. Scientists are on the lookout for these signals, and a big enough breakthrough would open a whole new window into the first seconds of cosmic history. Even for everyday astronomers, the discovery and mapping of the cosmic microwave background have made deep sky observations more precise. This background acts as a calibrator for instruments, and by understanding it carefully, astronomers can better subtract its effects to focus on faint galaxies, clusters, or supernova lying in front of this far background. In short, it's a foundation for almost all work in observational cosmology. The cosmic microwave background has even entered popular culture, with its mottled baby universe map sometimes appearing on coffee mugs, t-shirts, and textbooks. But even if you see it on a mug, those faint clouds and speckles are encoding real information. They mark the very beginnings of what would become vast cosmic structures billions of years later. If you ever gaze up at the night sky and imagine what's out there, know that every piece of light passes through a universe already shaped by the patterns in this ancient afterglow. It's hard to explain just how central the cosmic microwave background is to modern cosmology. Most big questions about the universe, its age, size, fate, contents, and structure, come down to interpreting this faint, uniform glow. Even the discovery that most of the universe consists of matter and energy we cannot see, like dark matter and dark energy, depended on careful studies of the background's tiny, precise temperature and polarization variations. By comparing the microwave background with the visible structure of the universe, galaxy positions, cluster shapes, and distances, astronomers have steadily built a consistent, reliable timeline that matches up with every other way we have of looking at space. Each time, technology gets a bit better and a new, more sensitive map is published. Cosmologists find new details that force the field to evolve. The basic details, an age of about 13.8 billion years, a temperature that has gently cooled ever since dust and gas formed the first atoms, a universe that started out nearly uniform but developed structure from tiny seeds, have stood up to all scrutiny so far. The Planck mission, as of its last results, gave the most precise measurements yet, and every new computer simulation or experiment shows just how vital the microwave background's information is. From a practical standpoint, the cosmic microwave background lets us cross-check concepts from particle physics, quantum mechanics, gravity, and astrophysics. It's the meeting point for dozens of different theories and experiments, all focused on explaining how a few thousandths of a degree fluctuations in the ancient universe could eventually lead to the rich diversity of stars, planets, and galaxies we see today. When astronomers discuss the echo of creation, they really do mean the leftover light from this once invisible phase shift of the cosmos going transparent. Ultimately, whenever you hear about a discovery relating to the universe's origins, its first galaxies, the growth of cosmic structure, or even the search for life elsewhere, a piece of that story traces back to the cosmic microwave background. This faint ancient afterglow is more than just a curiosity. It's the deepest, most enduring record of the universe's earliest ordinary light, a boundary that preserves the memory of a time when space itself changed forever. Every new project, each new survey, and all the cross-checked results come back to the same starting line, the microwave signature burned into the sky at the very dawn of everything we know. All of this careful work with the cosmic microwave background shows just how much of the universe's story is based on what we can actually detect. But there's something important that always comes up in these discussions. The universe we see is only a slice of what probably exists. No matter how sharp our telescopes get or how precise our measurements become, there is a hard limit to what's observable. Beyond this, there are regions of the cosmos that simply cannot be probed in any way, not now or even in the far future. This vast, hidden territory is known as the unobservable universe, and even though we can't see it, thinking about it helps us better understand the scope of everything we are part of. The boundary between the observable and unobservable universe is set by light itself. In practice, the edge is marked by the farthest distance from which any signal, light, radio waves, or any electromagnetic information could have reached Earth since the moment of the Big Bang. This sphere is called the observable universe, and its radius is about 46.5 billion light-years in every direction, so the diameter is nearly 93 billion light-years. But that does not mean the universe itself ends at that horizon. It just means that anything farther away has not had enough time, or will never get the chance, to send a signal that could reach Earth. There could be countless galaxies, stars, or even entire different cosmic structures outside that horizon, existing in a space forever hidden from our view. Our picture of the universe is constructed from everything inside this cosmic bubble. When you look outward, you see light from galaxies, quasars, clusters, and even the background radiation that formed about 380,000 years after the universe began. But anything farther out than that, that's completely invisible. In fact, because the universe has been expanding, many of those distant galaxies are moving away from us faster than light can travel, due to space itself stretching and not because they're breaking any rules of physics. The effect is that some regions, even if they shone with unimaginable brightness, are sending out signals that will never, ever reach us, no matter how long we wait or how advanced our instruments become. This idea comes straight out of the way space and time work on cosmic scales. The universe isn't static. Since the Big Bang, its expansion has been speeding up under the influence of something we call dark energy. That faster-than-ever expansion pushes some galaxies and regions of space over the so-called cosmic event horizon. This is a moving boundary. Once a distant object crosses it, it's cut off from us forever. Its light is always outpaced by the swelling universe, stranded in a region that cannot be connected to us by any future signal. The part that's almost hard to believe is just how much could be out there beyond what we see. Most major theories in cosmology suggest that the universe as a whole is far, far bigger than the part we can observe, possibly so large that it's effectively infinite. Some models point to regions so distant that even light travelling for the entire age of the universe would never reach us. It's even possible, according to some ideas, that there are entirely different portions or pockets of the universe with slight variations in their physical laws or histories. That leads to concepts like the multiverse, where our observable universe is just a single bubble among countless others, although there's no direct evidence for these ideas and they remain mostly theoretical. Also, it's not just about distance. Each part of the universe has its own observable bubble. If someone were living in a galaxy 50 billion light years from us, they would see a slice of the cosmos we can't, and some of the galaxies we see would be forever hidden from them. These different observable zones overlap but aren't identical from place to place. So the unobservable universe isn't just off in one direction. It wraps around us, forming the parts of reality that, from our point of view, are unreachable, but still possibly full of activity, matter, and history. The accelerating expansion, driven by dark energy, is a key reason for this inaccessibility. A galaxy passing beyond our cosmic event horizon could be seen today, but any signal emitted in the future from that galaxy would be stretched to infinite wavelength and would never reach us. That means some of the galaxies we observe now are already lost forever for any future observations. It's a strange situation. As cosmic time marches on, more and more of the universe drifts beyond our reach, and the observable bubble for any observer slowly empties out. You might be wondering why we should even bother talking about this unobservable universe if we'll never get evidence for what's really out there. The answer is that these ideas actually change how we interpret data from the part we can see. For example, the smoothness or lumpiness of the cosmic microwave background could be influenced by effects just outside of our cosmic horizon. Measurements of dark energy, dark matter, and the early history of the universe often depend on assumptions about what lies beyond. If the wider cosmos is very different on those large scales, our entire cosmological model might need correction. There are even more exotic suggestions floating around in current science. Some researchers propose that if the universe did go through a period of super-fast expansion, called inflation, right after the Big Bang, then regions far outside our observable bubble might actually look extremely different, or could even exist in a totally separate state. Different laws of physics, different types of particles, or a different arrangement of cosmic matter. It's a big leap, but some of these predictions can be partly tested by how patterns and cold spots in the cosmic microwave background appear, or by searching for rare clues like gravitational wave signatures that leak from beyond our horizon. It's also worth keeping in mind that even though the most familiar picture is of our observable universe as a perfect sphere centered on Earth, the real situation is more subtle. We're not the center of the full universe. Every observer sees their own horizon, shaped by their location and the age of the cosmos. So, while it looks like an edge to us, it's not a wall and not a sign that the universe itself ends. The structure, composition, and entire history could continue in every direction, completely unnoticed except for the slender slice of light that entered our telescopes. A part of the discussion about the unobservable universe focuses on the possibility of alien regions, areas with such different physical conditions that life, chemistry, and even the flow of time could work unlike anything familiar to us. Since we have no evidence from beyond our horizon, we can't rule these possibilities out. In theory, some cosmic models predict domain walls, or boundaries, where conditions switch abruptly, so in one area the laws of physics might just barely differ from those in our universe, maybe slightly different types of atoms, forces, or cosmic structures. This is one reason why cosmologists keep hunting for any oddities or hints at the edge of the observable universe that might signal a transition to something new. The ways scientists investigate the nature of what's unobservable mostly rely on indirect arguments. For instance, if inflation created all of space in one quick burst, then the cosmos could be infinite or nearly so, meaning that most of space is hidden from us forever. Or, if the universe is curved in a way we can't yet measure, then its total size and shape could be much stranger than we currently imagine. These large-scale ideas of geometry are constantly being re-examined with new data from background radiation maps, galaxy surveys, and cosmic distance measurements. The idea of the unobservable universe also affects the biggest questions about fate and origin. For example, the measured amount of dark energy and dark matter comes with some uncertainty. If these properties are different in the unobservable universe, then the cosmic fate, whether the universe keeps expanding forever, changes shape, or collapses, could actually play out differently than expected. Astrophysicists consider these out-of-sight regions in their calculations, especially when predicting the future motion of galaxies, the cooling of space, or the possible decay of dark energy. Some researchers have proposed that just as we are limited by our observable bubble, there may be objects or civilizations in the unobservable universe that have their own stories, galaxies, and possibly even observers wondering about life out there. It's one of those ideas that makes you appreciate how limited, but also how precious, our slice of cosmic history really is. We can measure, model, and guess, but the majority of the universe will always be just out of reach, both in terms of signals and direct interaction. For decades, physics and astronomy have tested whether there could be any communication beyond these observable limits. The answer, for now, is a solid no. No matter how powerful a detector is built, or how patient a scientist may be, the speed of light and the pace of the universe's expansion set an iron curtain against contact across that boundary. In principle, you could wait billions upon billions of years, and that outer universe would still always remain beyond the horizon, never sending so much as a single photon into our cosmic bubble. Mathematics and logic let researchers run simulations to see what might be possible in those unreachable regions. The results usually reinforce reinforce the idea that the larger universe is much the same as what we see, based on the uniformity of the cosmic microwave background and large-scale galaxy structures. But it's always possible, mathematically at least, that enormous surprises are hiding far away, and that in different distant domains, the basic ingredients of matter or light might behave slightly differently than in our patch of space. A small number of projects and telescopes try to probe the edges of what's visible using clever new techniques, looking for gravitational waves, capturing the rarest bursts of high-energy particles, or hunting for signals that could cross beyond the reach of regular light. Yet, their success will always be capped, no matter how revolutionary the technology or how sensitive the detector gets, by the finite age of our universe and its continually accelerating expansion. Even the fate of our own observable universe is shaped by what we cannot see. Eventually, if the expansion continues at its current pace or speeds up even further, the most distant galaxies visible to us today will slip away, redshifted into invisibility. In hundreds of billions of years, the cosmic microwave background itself will drift out of detection range. Future astronomers, if any exist, will have much less evidence to work with, being essentially cut off from any cosmic signals showing the universe's early days. The universe will become locally dark and quiet, with each observable bubble growing smaller and lonelier. While it's frustrating that we will likely never observe or contact the unobservable universe, this boundary actually helps anchor scientific thinking. It forces researchers to be honest about what the evidence shows and what it can never, even in principle, reveal. By knowing where the edge lies between testable knowledge and pure speculation, cosmology builds a solid foundation. Within these boundaries, the science has proved astonishingly successful in making accurate predictions, from the age of the universe to the behavior of galaxies and the fine details of background radiation. What is perhaps most intriguing is that some of the big mysteries in physics might get their answers from clues gathered right at this border. That last light, the faintest ripples in the background, or rare alignments of galaxies could all be hints about the structure of space just beyond our horizon. Teams of scientists continue to puzzle over whether tiny patterns in the cosmic microwave background or stretches of the cosmic web point to something deeper outside our visible universe. For all these reasons, the idea of the unobservable universe remains both a scientific challenge and a huge topic of curiosity. It is woven right into models of how everything began, how cosmic structure grew, and how the universe might someday end. Even without direct evidence, this invisible domain shapes how science is done today. It's a permanent part of our story, reminding us that just because we cannot see something does not mean it does not exist, and that the full map of reality may be vastly bigger than what our best telescopes, satellites, or calculations will ever uncover. In that sense, the unobservable universe is not just an empty direction in the sky. It's the biggest question in all of astronomy, always encouraging new ways of exploring, testing, and understanding everything we can see and everything that, for now, stays hidden just out of reach. For everything that's hidden outside our cosmic horizon, it's technology that decides how deep and how clearly we can see into our own observable universe. As good as today's telescopes and detectors are, we're always working up against some very real limits set by both nature and engineering on how far and how faint we can actually look. To understand just how much these limits matter, it helps to break down what makes seeing so far away so challenging, and how even cutting-edge observatories like the James Webb Space Telescope and the Hubble Space Telescope must constantly wrestle with the boundaries imposed by both physics and practical technology. The first and most obvious obstacle is distance itself. Space is filled with objects that are not only far away, but also incredibly faint, because their light has been spreading out for billions of years before arriving at Earth. For the Hubble or Webb telescopes to collect enough of that ancient light to capture even a blurry image, they sometimes have to point at one patch of sky for days or even weeks at a time. The famous Hubble Ultra Deep Field is a good example. During the early 2000s, astronomers focused Hubble on what looked like an empty region for more than 2 million seconds. About 23 days, and slowly the faintest, most distant galaxies emerged. But there's always a cutoff. However long you wait, there's a point where the signals become so faint they disappear into the background noise and random static of space. Then there's the fact that not all light makes it to us cleanly. as photons, tiny particles of light. From distant objects travel through the universe, they face obstacles. Intervening dust can absorb or scatter light, clouds of gas can block entire regions of the spectrum, and our own galaxy has massive clouds that turn areas of the sky dark or murky. By the time light gets through all that and arrives at Earth, it may have been dimmed or distorted. This is why ground-based observatories are often placed far from cities, on mountain peaks, or even in space. It means less atmosphere and less interference to block that precious ancient light. But even with the clearest view, all telescopes, no matter how sophisticated, run up against the brute fact of cosmic expansion. As the universe grows, light from the farthest objects gets stretched, turning visible light into infrared and eventually microwave. Space telescopes like Webb are built to observe in infrared exactly for this reason. Still, even their detectors can only go so far because there's a hard wall set by the cosmic microwave background. That's the point where the universe became transparent, and anything before that time just isn't accessible with normal telescopes, no matter how sensitive. One major technical limit is the size of the mirror or lens being used. Bigger is better because a larger mirror collects more light. The Hubble's main mirror is 2.4 meters wide, while James Webb's golden mirrors spread 21 square meters. The wider the mirror, the fainter the object you can see and the sharper the image. But making these giant mirrors is a monster of engineering. They need to be nearly perfect, smooth to the precision of fractions of a wavelength of light, and free from flaws or warping, or else the final image turns fuzzy. Building, launching, and then unfolding a mirror as complex as James Webb's is why it took more than 20 years, thousands of workers, and a price tag of nearly $10 billion. Another challenge is the range of wavelengths a telescope can detect. Different objects in the universe shine at different wavelengths, from radio waves to visible light to X-rays and gamma rays. Earth's atmosphere blocks much of this radiation, which is why we put telescopes on satellites or in very high, dry places. The Hubble is mostly sensitive to visible and near ultraviolet light. James Webb is optimized for infrared, the best region for catching faint, distant, red-shifted galaxies from the early universe. Radio telescopes, like those used for mapping cosmic background or hunting for pulsars, need huge dishes to detect longer wavelength signals. But every detector design has limits, and some parts of the spectrum never reach the ground and can only be detected above the atmosphere. Even when telescopes catch the light, they have to turn that signal into usable data. State-of-the-art detectors like CCDs for visible light or specialized sensors for infrared must be cooled to extremely low temperatures to minimize static and background noise. Any stray light, heat, or even the telescope's own electronics can swamp the faint signals from ancient galaxies. Cooling a detector for years at a time, way out in space, is a huge technical challenge and has led to months or years of extra development for every serious infrared observatory. There's a different sort of limit too, the background glow set by things closer to home. Even out in the vacuum of space, there's a soft fog set by glowing dust from our own solar system, or distant galaxies we can't resolve individually, but whose combined light enters every shot. This is called background noise, and trying to subtract it from the real, meaningful signals is painstaking work. Too much background, and faint galaxies or stars get totally lost in the glare. Sometimes cosmic expansion and physics team up to impose a special kind of observational wall. When mapping the universe's structure using galaxies or supernovae, you hit what's called the cosmic variance limit. This means you can only study the universe's biggest features within your own observable patch. Nothing outside that region will ever be visible, and anything you see at those far edges becomes a kind of statistical guess. Every time you look deeper, samples get smaller and predictions are less precise. While we can't see directly past the cosmic microwave background, astronomers are experimenting with new kinds of messengers: gravitational waves and neutrinos. Gravitational wave detectors like LIGO and Virgo catch tiny ripples in space caused by massive events like black hole collisions. These waves can pass through matter and travel vast distances, but the detectors are sensitive only to really dramatic events. There are also plans for space observatories to sense gravitational waves at different frequencies, potentially opening another window on the far reaches of the universe. Still, the same rules apply. Gravitational waves, like light, take time to travel, and cosmic expansion sets new limitations on what we could ever detect. Neutrinos, tiny, nearly massless particles, are another possible window. Billions of them pass through your body every second, but they barely interact with anything. Massive underground detectors filled with special liquids or ice are used to spot just a handful of cosmic neutrinos. These particles have the potential to give information from sources deep inside stars, or even the first seconds of the universe. But again, even neutrino detectors have background noise, energy thresholds, and engineering barriers. In recent years, one way around the slow pace of gathering deep images has been through vast digital sky surveys. Projects like the Sloan Digital Sky Survey or the upcoming Vera C. Rubin Observatory make it possible to scan huge portions of the sky night after night, capturing transient events and faint galaxies all at once. These surveys produce more data than anyone could manually process, sometimes tens of terabytes every night, so teams use artificial intelligence and careful calibration just to make sense of it all. Yet, huge digital surveys can still only see as far and as faint as Earth's sky, the instruments and the cosmic expansion will allow. Anything that happens beyond the reach of the survey's cameras, or is blocked by gas, dust, or the microwave background, remains a blank spot. Special telescopes use adaptive optics, bending their mirrors in real time to correct for tiny changes in the air above them and sharpen their focus. Still, even the best adaptive optics on Earth can't totally erase the blurring caused by thousands of kilometers of atmosphere, which is why telescopes like Hubble and Webb above the air make such a difference for ultra-deep space. On the radio astronomy front, scientists have learned to combine the signals from many smaller dishes scattered across continents, creating an effective telescope as wide as the Earth, or even larger when they coordinate space-based radio dishes. Another important detail is cosmic time. Some signals we'd like to study, the first moments after the Big Bang, the birth of the first stars, are hidden by the fact that either they never released light we could detect, or that expansion has erased their signal. Others are drowned by more recent and brighter cosmic events, meaning you need to catch certain signals at exactly the right time, or they'll be overwhelmed by everything else in the universe. Cosmic rays present another source of information, but also of interference. High-energy particles from space slam into our detectors all the time, sometimes leaving a blip or even causing damage to the most sensitive cameras. Telescopes must be designed to block, shield, or account for these cosmic rays when measuring super-faint distant sources. Astronomy is also limited by the practicalities of funding, politics, and even the laws of physics that govern rockets and engineering. Getting a telescope into space is an expensive, risky project. Many proposals never get built, and every delay or technical problem means some questions about the universe have to wait. Meanwhile, instruments in space age with time. Batteries lose power, electronics fail, sensors degrade, and the ability to make repairs is limited. Hubble, for example, was famously fixed by the space shuttle, but that's rarely possible. James Webb is too far away to ever be serviced. For everything we can see and measure, there's always more detail just out of reach. Even in galaxies nearby, parts of the universe are hidden by dust lanes or regions so dense and bright that telescopes can't resolve individual objects inside them. Black holes themselves, by their very nature, create true observational gaps. It is literally impossible to see inside the event horizon, so anything that happens beyond that boundary must be inferred from clues at the edge. When it comes to detecting exoplanets, planets orbiting other stars, there are also major observational hurdles. The glare from the host star usually drowns out any light reflected or emitted from the planet itself, making direct images of smaller, Earth-like worlds extremely difficult. Instead, astronomers mostly rely on indirect detection, watching for tiny dips in starlight as the planet passes in front, or measuring the way a star wobbles due to a planet's gravitational pull. While this has led to thousands of discoveries, most of the exoplanets found are much bigger or much closer to their stars than Earth because those are the easiest to spot. There are always hopes that with a breakthrough in computer processing or a new kind of detector, the boundaries will move. Every new marvel, like Webb or the upcoming telescopes in Chile and Hawaii, pushes a little deeper into the dark, letting us glimpse further into the dark space and further back in time. But however much progress is made, the constraints are set by a mix of cosmic circumstances, engineering, and even human cooperation. Despite all these limits, what's been achieved so far is genuinely staggering. From seeing the faint first galaxies more than 13 billion light-years away, to mapping the afterglow of the Big Bang, and now to catching the mergers of black holes and neutron stars by their gravitational waves, telescopes and detectors keep adding new layers to the story of the cosmos. Advances in quantum detectors, bigger and lighter mirrors, smarter algorithms, and new ways of filtering out noise mean every generation of astronomers sees further, sharper, and faster than the generation before. But as of now, there's already evidence that some mysteries will remain out of reach no matter how clever we get. The edge marked by the cosmic microwave background, the event horizons of black holes, and the speeding expansion pushing whole galaxies beyond detection are as far as science can go under the current laws of physics. Some signals or objects are just too faint, too distant, or blocked by too many cosmic obstacles to be known directly. Knowing these limits is actually a strength rather than a weakness for astronomy and cosmology. It helps scientists to be honest and precise about what they really know, what's based on direct evidence, and what's still a matter of best guesses or creative theory. Every measurement comes with error bars and a note about how it was obtained, reminding everyone that none of our images, however amazing or beautiful, offers a full and perfect account of what's out there. It's always a work in progress. In the coming years, all eyes are on new telescopes that may break one boundary or another, or use the universe itself as a lens to see further. Projects that combine radio, optical, X-ray, and even gravitational wave signals are building a multi-messenger view of space, letting us cross-check and compare different types of evidence from the same cosmic event. These new tools bring promise, but also come with the same unyielding cosmic and technical barriers. After centuries of progress, it's clear that technology and ingenuity can push the horizon back, letting us explore more of the observable universe. But the mixture of cosmic expansion, intervening material, detector limits, funding, and engineering will always mean that some places remain unseen and some questions remain open. That's all part of exploring a universe as vast, ancient, and complex as ours, a story shaped as much by the places we can reach as by those always just out of view. Every improvement in telescopes and observation methods lets researchers add more detail to the cosmic map, and these breakthroughs have revealed that the universe isn't a random scatter of galaxies in every direction. When astronomers zoom out to look at the largest scales, what they find is this incredibly intricate network. Clusters of galaxies packed together, thin bridges called filaments stretching between them, and giant, nearly empty regions called voids. This type of cosmic structure is a key part of the universe's story because it shows how matter has organized and shaped itself since the earliest days after the Big Bang. These patterns aren't just interesting to look at, they hold crucial clues about gravity, dark matter, and the overall evolution of everything we see in space. Most people imagine galaxies as isolated islands in the cosmic ocean, but the truth is, no galaxy is really alone. Take our own Milky Way, for example. It's a member of a relatively small group called the Local Group, which also includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller ones. But if you keep pulling back the scale, the Local Group itself moves as part of a much larger cluster called the Virgo Cluster, which contains thousands of galaxies. On even bigger scales, clusters are tied together by massive filaments, sort of like the strands of a three-dimensional spider web, weaving their way through space for hundreds of millions of light years. The points where these filaments meet are where you'll find the greatest clusters, true cities of galaxies numbering in the thousands. These clusters didn't just pop up overnight, they are the end products of gravity's long work, slowly pulling together smaller systems over billions of years. When the universe was very young, matter was much more evenly spread out. But even in those first stages, tiny fluctuations in density, just a part in 100,000, acted as seeds. Over time, gravity took effect. Wherever there was a bit more matter, it pulled together even more matter, creating denser and denser regions. Those original seeds grew to become galaxies, then groups, then clusters. Eventually, as these clusters merged and grew, they turned into the large-scale structures we can see with surveys like the Sloan Digital Sky Survey or images from telescopes like Hubble. If you were to travel across the universe, it wouldn't feel like flying through a solid wall of galaxies. Instead, you would spend most of your journey passing through vast, empty regions, the voids. These voids can be 100 million light-years across or more, and they contain almost no galaxies at all, maybe just a few wandering dwarfs or thin traces of gas. In every direction, these voids separate the much busier downtown regions of the cosmic web. It's within the filaments and at their crossroads that the action happens, with galaxies forming stars, merging together, and groups of black holes and clusters swapping members as gravity continues to work. The biggest structures identified so far are things like the Sloan Great Wall and the Hercules Corona Borealis Great Wall. These aren't actual walls, but more like giant chains or sheets of galaxies and clusters that stretch across more than 1 billion light years. It's almost impossible to imagine the scale. You'd have to line up millions of galaxies to match the size of just one of these structures. The fact that such giant formations exist was a surprise to many astronomers because they push the limits of what we expect from standard models of cosmic evolution. They show that, given enough time, gravity can shape matter into unbelievably vast configurations. Closer to home, the local group and its neighbouring clusters are connected to the Virgo supercluster, a gigantic arrangement of more than 100 groups and clusters of galaxies. Even this is just one branch of the much bigger Laniakea supercluster, Laniakea meaning immense heaven in Hawaiian. This cosmic continent contains tens of thousands of galaxies and, by present measurements, stretches well over 500 million light-years. Our own Milky Way is only a small part of this tremendous network, orbiting in a region shaped by both the gravitational pull of the Virgo cluster and a huge void called the local void. But how do astronomers really map and study these cosmic structures? They use a combination of redshift surveys, which measure how much the light from galaxies is stretched by cosmic expansion, and deep imaging at visible, infrared, and radio wavelengths. These surveys determine how galaxies are spread out over billions of light years and reveal where the densest filaments and biggest voids lie. The resulting maps look nothing like a flat or random arrangement. Instead, they resemble a foamy or web-like pattern where clusters appear as bright nodes and filaments connect them with thin bridges filled with smaller galaxies and dark matter. Gravity is the main force driving the growth of these structures, but there's more than just ordinary matter involved. The hidden presence of dark matter, which accounts for roughly 80% of all matter in the universe, creates the invisible backbone of the entire cosmic web. Simulations run on supercomputers show that without this dark matter, detected only through its gravitational effects, clusters and filaments would never have formed in time. Dark matter acts like scaffolding, attracting regular matter into long streams that later light up as stars and galaxies. The visible universe, then, is really a glowing outline filled in along these dark matter frameworks. The role of dark matter becomes obvious when you measure the motions of galaxies within clusters. Galaxies move much faster than they should if all the mass was coming from the stars and gas we can see. The extra mass is attributed to vast halos of dark matter, which act as cosmic glue. The largest clusters are surrounded by superhalos of dark matter spanning millions of light years, providing the deep gravitational wells where thousands of galaxies can orbit and interact over billions of years. Inside clusters, galaxies can even collide and merge, producing bursts of star formation or feeding huge black holes at their centers. Clusters themselves are filled not just with galaxies, but also with hot plasma, gas heated to tens of millions of degrees, glowing in X-rays. All of this motion and activity helps astronomers measure the cluster's total mass and compare it with how much ordinary matter they can see, confirming that most of the weight is actually in invisible dark matter. Filaments, which bridge clusters and cross enormous distances, are just as intriguing. Most are only a few million light years wide, but stretch for up to hundreds of millions of light years. They form along the paths where matter has fallen together, and computer simulations show that the slow collapse of dark matter and regular matter together leads to the building of these superhighways. Along these filaments, galaxies slowly migrate toward clusters, and the positions where several filaments meet are among the most massive and active places in the universe. The mapping of filaments is often done by tracing both visible galaxies and faint signals from diffuse gas, sometimes detected in radio or X-ray light. Galaxies in filaments don't just stay put, they're pulled towards the denser nodes at the intersections, like beads rolling down a wire. Over billions of years, this creates a steady flow of galaxies into clusters, where more collisions, mergers, and bursts of new stars take place. Even the shape and rotation of galaxies can be shaped by their journey through filaments and cluster environments, showing that location in the cosmic web affects everything from star birth rates to the growth of supermassive black holes. The voids, those empty regions between filaments, are just as important. While mostly dark and quiet, they act as the balance to the universe's structure, separating clusters and filaments and influencing their growth. Some of the largest voids are so big that once a galaxy drifts in, it might not meet another for hundreds of millions of years. The density of matter in these voids is so low that what little gas exists moves extremely slowly, and very few stars are born there compared to the rich environments closer to clusters and filaments. Discovering and measuring these voids has helped cosmologists test the predictions of dark energy and cosmic expansion. Void regions expand slightly faster than the rest of the universe because there's less gravity to slow them down. Recent surveys using tens of millions of galaxy positions have mapped thousands of voids, some up to 300 million light-years across. These vast empty spaces are not just the absence of galaxies, but whole patches of the cosmos with unique properties, such as cooler temperatures and different patterns of matter distribution. The study of cosmic structure also helps refine theories about the early universe. The initial lumps and voids seen in the cosmic microwave background were magnified and stretched by gravity into the clusters, filaments, and voids we see today. Scientists use massive computer models to start from those first tiny variations and build up simulated universes, comparing them to actual surveys to test if their understanding of physics matches reality. The excellent agreement between simulated and observed structures supports all kinds of measurements, like the amount of dark energy and the age of the universe. Interestingly, not all structures are permanent. Clusters can change as galaxies fall in, merge, or get pulled out by nearby structures. Filaments can become thicker as they absorb more matter or break apart if cosmic events disperse their contents. Voids can shrink or grow, depending on the flow of galaxies nearby. Mapping these changes tells astronomers how fast the universe is evolving and provides hints about what it will look like billions of years from now. Sometimes astronomers spot unusually large or dense clusters, or extremely long filaments that challenge models or predictions. These are studied very closely to see if something new is happening, maybe a particularly massive concentration of dark matter or signs of past cosmic mergers. Each discovery like this helps refine the models and might even hint at new physics beyond what is currently known. The biggest picture from all of this work is that the universe, on its grandest scales, shows repeating patterns of structure, clusters that grow by merging, filaments that act as highways for matter, and voids that are the backdrop for all motion and growth. These shapes are determined by gravity and the initial scattered seeds from the early universe. Over cosmic time, they keep evolving as the universe itself expands and changes. So all those deep surveys and ultra-sensitive observations have given us a clear view of something remarkable. The cosmic web is not just a way to describe how things are distributed, it's the blueprint for how the universe works. It explains why galaxies gather, how clusters grow, and why vast stretches are almost empty. It shows that structure, not chaos, shapes the fate of everything in space, giving us a cosmic architecture drawn on the largest canvas possible. Understanding these patterns helps with everything from measuring the universe's age and size to tracking down the mysterious nature of dark matter and energy. Each new map, deeper survey, or sharper image fills in a piece of the puzzle, showing a universe at once organized and full of surprises, where every cluster, filament, and void is another chapter in the long history of cosmic evolution. While all of this structure, clusters, filaments, and those enormous voids provides a physical map of the universe, the more astronomers study it, the more obvious it becomes that most of the universe isn't even visible. For every bright galaxy or glowing cluster in these cosmic webs, there's an even greater amount of stuff we can't see directly. This takes us straight to two of the universe's most baffling ingredients: dark matter and dark energy. These topics might sound mysterious, and that's not just because they're invisible. It's because they make up almost all of the cosmos, yet remain among the greatest open questions in modern science. To break it down, let's start with what's visible and familiar. The stars, gas, dust, and planets that we see in the night sky, everything that gives off light or can be detected by telescopes, make up roughly 5% of the entire universe. That's it. The rest is hidden away. Dark matter accounts for about 27%, and dark energy takes up around 68%. Knowing these numbers comes from decades of evidence collected from how galaxies spin, how clusters move, and how the cosmic web grows over time. Dark matter first came into the conversation in the 1930s, when astronomers noticed that galaxies within clusters were moving faster than they should, based on the gravity from visible matter alone. Fritz Zwicky, observing the Coma cluster, pointed out that there had to be more mass holding the cluster together, otherwise those galaxies would simply fly apart. He called it dunkle materie, or dark matter. Later, in the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found that stars far from the center orbit just as fast as those near the middle. The speeds didn't drop off the way physics predicted if you only count visible mass. There was only one conclusion: something unseen, providing extra gravitational pull, surrounds every galaxy, making a massive, roughly spherical halo that extends far beyond the edges of the galactic disk. Now, dark matter doesn't emit, absorb, or reflect light, which means ordinary telescopes can't pick it up, but its presence can be inferred in a bunch of ways. Besides those galaxy motions, you can also see its effects during gravitational lensing. This is when the light from a faraway galaxy is bent by the gravity of massive clusters in between. The amount of bending is often much more than the visible mass could create. Observing the paths and magnification of these lensed galaxies, astronomers can weigh the invisible mass, confirming huge amounts of dark matter in clusters, filaments, and even within galaxies. Dark matter is also crucial for shaping the universe's large-scale structure. When scientists run computer simulations starting with the universe just after the Big Bang, the only way to get realistic clusters and filaments by the time billions of years have passed is to include enormous amounts of dark matter. It acts as an invisible scaffolding, helping regular matter clump together to form galaxies. Without it, the universe would be much more spread out and much less structured. Patterns in the cosmic microwave background also fit with a universe filled mostly with this invisible material. What about dark energy? This is even stranger. In the late 1990s, two independent groups, using observations of supernovae, which are exploding stars that can be seen at enormous distances, found something nobody expected. The expansion of the universe wasn't slowing down due to gravity as everyone thought. Instead, it was speeding up. All the galaxies, already moving apart due to cosmic expansion since the Big Bang, were pulling away from each other even faster every year. Whatever is causing this extra push is called dark energy. It acts as a sort of anti-gravity, working against attraction and making the fabric of space stretch at a growing pace. The discovery of dark energy transformed cosmology overnight. Now, when scientists talk about the fate of the universe, predictions depend much more on this unseen energy than on all the visible matter combined. Measurements from the cosmic microwave background, galaxy surveys, gravitational lensing, and even distant explosions all match up with a model where dark energy is the main driver in today's universe. Despite their names, dark matter and dark energy aren't related in any obvious way, except that both are dark, meaning invisible to light and undetectable except by their impact on gravity or the universe's expansion. Scientists think dark matter might be a new kind of particle. Some theories point to weakly interacting massive particles, sometimes called WIMPs, sterile neutrinos, or even more exotic things, but so far no particle detector on Earth has found solid proof. Massive underground experiments in Europe, North America and Asia are all constantly on the lookout for these rare interactions. As of now, all the evidence for dark matter remains indirect. Gravity, lensing, cosmic structure, and galaxy motions. For dark energy, the leading explanation is even less concrete. The most accepted idea is that it comes from the vacuum energy of space itself, sometimes called the cosmological constant. This is a boring-sounding term for a weird property. Even empty space with nothing in it has a tiny amount of energy that adds up over vast stretches, and because of the way gravity works in Einstein's equations, it produces a repulsive effect. Another possibility is that dark energy could change over time or come from some new field, like quintessence, a term for a hypothetical evolving energy field. But with only one universe to study and all the effects added together, it's incredibly hard to pin down what's really going on. If dark matter is the invisible skeleton holding the universe together, dark energy is the hidden force stretching it apart. Working together, these shape the past, present, and future of the cosmos. For example, if dark energy remains constant or even grows, eventually galaxies will speed away from each other so fast that even their faint light won't reach us anymore. Within tens of billions of years, our own group of galaxies might be the only thing left that we can see, with the wider universe redshifted into invisibility. The expansion will continue pushing things farther and farther apart, with less and less chance for new cosmic events to reach us. There are also deeper implications for the structure and fate of everything. without dark matter, no galaxy clusters or filaments could form as quickly as we see them in the sky. Galaxies wouldn't have grown so large, and the web-like structure that fills the universe would be much fainter and less connected. On the flip side, if dark energy were stronger in the early universe, expansion might have ripped apart even those clumps, stopping galaxies from forming altogether. Astronomers and physicists worldwide use dozens of methods to measure and test the properties of dark matter and dark energy. They examine how galaxies rotate at all distances, how cosmic microwave background fluctuations add up at different scales, and how the large-scale baryon acoustic oscillations, sound wave ripples from the early universe, match predictions. They also compare observations from galaxy clusters, supernovae, and the way distant light gets bent by gravity. Each of these tools helps to further limit what these invisible components can be, how much is present, and how they might change with time. There have been creative attempts to find direct evidence of dark matter particles. For example, the Large Hadron Collider in Switzerland has searched for new particles in high-energy collisions, hoping to spot something that matches the expected properties of dark matter. There are also giant underground detectors filled with liquid xenon, germanium, or other materials, trying to catch the incredibly rare moment when a dark matter particle might interact with an atomic nucleus. Unfortunately, as of the early 20s, no candidate has yet been found. Sometimes unexpected signals appear in the data, but none have withstood deeper investigation. With dark energy, the situation is even trickier. Since it's not a particle and acts evenly across all of space, there's no direct experiment to catch it. Instead, all the measurements come from how the universe expands over time. Precise maps of galaxies at different epochs, meaning different look-back times, reveal how the expansion rate changes. The Planck satellite, which measured cosmic microwave background variations with incredible accuracy, strongly supports the existence of dark energy, agreeing with results from thousands of supernovae and the layout of galaxy clusters. One reason everyone is so interested in these mysteries is that if we ever figure out exactly what dark matter or dark energy is, we'll have deeper insight into the basic laws of nature. Solving these mysteries could open the door to new types of physics, new particles, or explanations for why the universe looks the way it does. It might even connect to ideas about extra dimensions or other universes beyond our horizon, though those remain speculative for now. There are some ongoing debates in the scientific community about just how constant or simple these dark components are. As telescopes get more sensitive, some measurements of the Hubble constant, the current expansion rate of the universe, don't quite match up, depending on how and where you measure. This might hint at new physics, or perhaps complexities we don't yet understand, in either how dark matter behaves or how dark energy evolves. Researchers are hoping that new surveys like those from the Vera Rubin Observatory or the European Euclid mission will help clarify these differences by mapping billions of galaxies across cosmic time. Every time researchers publish new measurements, theorists try to work their discoveries into better models. Sometimes there are surprises. Gravitational lensing maps have revealed weird, dense clumps of matter with little or no light, likely large clouds of dark matter. In a few galaxy clusters, astronomers have seen clear separation of visible gas and dark matter after two clusters collided, providing dramatic, direct proof that dark matter and normal matter can behave very differently under extreme conditions. None of these results point to dark matter or dark energy being something ordinary. No faint stars, no hidden black holes, and no wanderers we've missed so far. These unseen components have to be genuinely new stuff, not just things already known from regular physics. This is why the hunt continues for faint interactions, slight hints in cosmic rays, or subtle differences in gravitational waves from far-off collisions. Dark matter and dark energy even show up in our own galaxy. The rotation curve of the Milky Way, the motion of nearby dwarf galaxies, and the speed of stars all point to a halo of dark matter surrounding everything we can see. Some predictions suggest that, on rare occasions, a dark matter particle might hit an atom here on Earth, depositing a small bit of energy. So far, the detectors haven't caught this, but experiments are becoming more sensitive every year. One of the most powerful pieces of evidence for dark energy comes from galaxy clusters. By counting how many clusters form at different times in the universe's history, scientists can see that something is working against gravity, suppressing the growth of new clusters at later times. This matches predictions for a universe dominated dominated by dark energy, where the expansion speeds up and galaxy making slows down. The cosmic microwave background, which records the earliest days of the universe, is also influenced by both dark matter and dark energy. Tiny ripples in this background, measured to accuracy of millionths of a degree, match what would happen if dark matter provided most of the gravitating mass while dark energy drove late-time acceleration. The shapes of these ripples, called acoustic peaks, give direct evidence for the balance of all three components: visible matter, dark matter, and dark energy. Supercomputer simulations continue to test ideas about these invisible ingredients. Starting with different amounts of dark matter and dark energy in a digital universe, researchers can watch what happens to forming galaxies, clusters, and filaments. The simulated patterns either do or don't match what's seen in the sky with large surveys. Over the last 2 decades, these comparisons have consistently reinforced the basic numbers. Dark matter and dark energy clearly dominate by far, even if their detailed nature remains out of reach. Many scientists are also testing more radical ideas. Maybe gravity changes its rules at certain distances or energies, or perhaps our current theories need big updates. Alternative models keep being proposed, and some are tested with new data. Still, as of the year 2024, the standard model, called lambda CDM for cosmological constant plus cold dark matter, explains the shape, age, and makeup of the universe better than anything else so far observed. The more we learn about the universe, the more certain it is that the visible part is just a tiny slice of what's out there. Mapping and measuring dark matter and dark energy lets scientists understand structure, galaxy growth, cosmic expansion, and even the ultimate fate of everything. As technology gets better, surveys go deeper, and new messengers like gravitational waves join the hunt, there's hope that new evidence could finally shine light on these cosmic mysteries. Until then, dark matter and dark energy remain the shadowy but indispensable foundation for the universe's evolution and all the wonders we observe around us. For as much as dark matter and dark energy define what the universe is made of and how it will evolve, there's another scale that keeps coming up when we try to push the limits of our knowledge. The possibility that everything we know is just a piece of something even more vast. When scientists start thinking about what might lie beyond our observable patch of space, the numbers get bigger and the ideas get wilder. The possibility that the universe could be infinite, or that there could be multiple universes, each with their own rules, has gone from science fiction territory to serious, ongoing scientific discussion. This is where imagination and science have to work side by side, because there's no telescope, no matter how advanced, that can show us these regions directly. Starting right from the edge of the observable universe, we're already talking about distances so enormous that even light has not had time since the beginning of everything, about 13.8 billion years ago, to travel to us from farther away. Remember, our observable bubble has a radius of about 46 billion light-years because of cosmic expansion, so the full diameter is more than 90 billion light-years across. But most current models suggest that what we see is just one patch in a total cosmos that expands much farther than that bubble. There's no solid evidence that the universe suddenly stops where we can no longer see. There are likely to be more galaxies, more clusters, and potentially endless space beyond, all unreachable to us simply because the signals haven't had enough time to reach us, and, in some cases, never will. One reason astronomers are comfortable discussing an infinite universe is the observation that, despite all the structure and local differences, things look pretty much the same everywhere. This cosmological principle means the laws of physics, the density of matter, and the broad patterns of the cosmic web look basically the same in every direction. When researchers map the universe using the farthest galaxies, the patterns of the cosmic microwave background, or the positions of galaxy clusters, they don't find any edge or sign that things just stop. All the data within our bubble points to a cosmos that either has no edge or wraps back on itself in a way that we can't detect with current surveys. But if the universe is infinite, what does that mean in practical terms? First, it means that the story we tell using our telescopes only covers a tiny fraction of everything that's out there. For every galaxy we can count, there may be countless others following the same laws of gravity and expansion, but forever outside direct observation. If the spectrum of possibility is really endless, then the history, organization, and even future of the universe go beyond what any human or machine will ever access. It could even mean that while our patch of space has structures like the Milky Way, the Virgo cluster, or the Laniakea supercluster, the same kinds of features could play out over and over, far beyond any horizon. Taking things even further, some ideas suggest that not only could space be infinite, but the rules themselves could change from place to place. The multiverse idea is one of the most debated possibilities in all of science. In this picture, what we think of as our universe is actually just one region among many, possibly with different values for what astronomers call fundamental constants. Some parts of the larger cosmos might have different strengths of gravity, masses of particles, or combinations of dark matter and dark energy. Others might not even resemble our universe at all. They could be dominated by different forces or types of matter, or even operate under different numbers of dimensions. The reason scientists take these wild-sounding ideas seriously comes partly from the theory of cosmic inflation. According to inflation, in the first trillionth of a second after the Big Bang, the universe expanded much faster than the speed of light. This expansion ironed out any wrinkles or irregularities and left behind regions that could be billions of light-years apart, or even entirely disconnected from each other. Some models of inflation suggest that this process might continue in other faraway regions, spawning bubble-like universes with their own beginnings. If that's right, then the multiverse is not just possible but even expected, and our own observable universe is just a local neighborhood in a much, much larger reality. There's also the possibility that if space is infinite, and if the laws of probability play out everywhere, then there could be endless versions of galaxies, stars, even planets much like Earth, or much unlike ours, in other regions we'll never reach. This isn't just an idle guess. If the universe is infinite and the initial conditions are random, then mathematical probability says that every allowed configuration could happen somewhere. That's how some scientists get to discussions about infinite versions of solar systems, or even versions of ourselves, though that goes far beyond anything that can be tested with current physics. All of this sounds like it's heading into pure speculation, and for now, without direct evidence, most of it remains in the realm of thoughtful possibility, not solid science. But there are a couple of real, meaningful ways this thinking shapes current research. First, if the universe is infinite, astronomers must be careful about how they define the average properties of anything, since averages over infinite regions behave very differently from those in a closed, finite system. This comes up in studies of cosmic microwave background, the fate of dark energy, or predictions about gravitational waves from the early universe. Second, every time cosmologists map the universe and find uniformity, where the same physical laws seem to apply everywhere, it boosts confidence that our patch is not unique. Finding oddities or breaks in this pattern is legitimately exciting because it could mean a transition to something else or a signal from a real cosmic edge. But so far, those surprises have not shown up. Some astronomers look for footprints or indirect hints that might suggest a bigger universe or even a multiverse. These can come in the form of unusual alignments or cold spots in the cosmic microwave background, patterns that appear strange compared to what's predicted by the standard model. Another example is the so-called axis of evil, a somewhat tongue-in-cheek term for a large-scale alignment seen in some maps of the cosmic background. So far, none of these observations has been accepted as proof, but they push researchers to keep testing, updating, and questioning their assumptions. Another angle relates to the fine-tuning of physical constants. The fact that gravity, electromagnetism, nuclear forces and all the rest have the just right values needed for stars, galaxies, and life to form gets attention. In an infinite or multiverse universe, every possible combination could exist somewhere, and perhaps ours is simply the region where life can develop. It's a way to think about why the universe allows for complexity, though it's still debated just how meaningful this is without more evidence. It's also interesting to consider that even if the universe isn't truly infinite, but simply very, very, very large, the basic ideas don't change much for practical astronomy. With current technology, humans will never physically reach the edges of the observable universe, let alone anything farther. Light from those outer regions will always be blocked by the twin barriers of limited cosmic time and the fact that space keeps expanding. So whether the total is infinite or just so huge that we can't measure it, our perspective remains effectively the same, limited to interpretation and careful speculation speculation based on what we can verify. There are ongoing efforts to make these huge questions testable. For example, teams are simulating what sort of features or cosmic patterns might show up if there are contacts or overlaps between different universes, or if inflation created unique signatures in the background radiation. They hunt for subtle gravitational effects, rare cosmic particles, or even waves in the early universe that might hint at processes beyond our patch. None of these efforts has yet revealed clear evidence, but every year brings new data and new chances to challenge or support the predictions. Discussions about other universes often overlap with big ideas about quantum mechanics, space-time geometry, and the fate of everything. Some theoretical physicists imagine that every quantum event could spawn a new universe. That's one version of the multiverse, though completely different from the one tied to cosmic inflation. Here again, imagination does most of the work, but the math helps describe what could happen if the rules of physics are extended to the biggest canvas imaginable. In recent years, space missions and surveys have improved indirect checks on the shape and size of the universe. With careful measurements of the geometry of cosmic microwave background, the spectrum of baryon acoustic oscillations, and the clustering patterns of billions of galaxies, researchers can check whether the geometry is flat, open, or closed on the largest measurable scale. So far, results are consistent with a flat universe to high precision, which suggests that either the entire cosmos is infinite or so large that the curvature is undetectable by any practical means. At the same time, every new discovery adds to the library of cases supporting that our piece of space is typical for what's possible in cosmic evolution. New telescopes and detectors, like James Webb or the planned next generation of wide-field surveys and radio arrays, might eventually spot faint evidence of something that hints at a truly vast or strange universe. But as of today, nothing has shown a clear sign of breaking the rules established by the Standard Model, with all the contents, history, and features matching the predictions of a universe governed by the same suite of natural laws. Thinking about the infinite cosmos or other universes also puts a fresh light on ideas about time, fate, and cosmic evolution. If the universe is infinite and dark energy keeps pushing galaxies apart, then every region will eventually become more and more isolated. For astronomers of the distant future, tens or hundreds of billions of years from now, the sky will actually look emptier and lonelier as galaxies speed away faster than light and disappear from view. All the clues that tell us about the early universe, such as the cosmic microwave background or evidence of galaxy formation, will fade and eventually become inaccessible. This is a real and unavoidable trend if our current ideas about expansion hold true. One place where all these questions come together is the search for a unified physical theory. Since the 1980s, some physicists have hoped for a model that combines general relativity, our modern theory of gravity, and quantum mechanics into a single framework. Some versions of these theories of everything predict extra dimensions of space, hidden types of matter, or even natural mechanisms for generating many universes. This is another factor driving interest in what lies beyond our own cosmic horizon. Solving big-picture physics relies on having the most complete context possible. Ultimately, whatever the final answer might be, the very effort to imagine what's beyond our universe's edge is rooted in the human drive to explore and make sense of the biggest questions. Astronomers and physicists keep pushing for deeper surveys, new kinds of detectors, stronger computational models, and broader international cooperation to get the clearest possible view of reality. Every result, whether it matches prediction or points to something new, adds to the foundation of knowledge and opens up fresh paths for further exploration. Right now, all the evidence points to a cosmos that is vast beyond direct measurement, with more wonders, galaxies, and mysteries than anyone could ever catalogue. Even if infinite or truly plural universes remain an open question, the process of seeking answers keeps reshaping our understanding of space, time, and what might one day be possible. The unexplored universe isn't just a distant horizon, but a standing invitation for curiosity, careful testing, and scientific creativity on the grandest scale.